Hi, in this video we're going to talk about centripetal force. If you like these videos, please tap the like button. Tapping the like button will help reach a wider audience. And also please subscribe. Thank you for watching. All right, now let's look at motion in a vertical circle. So in this situation, I have a ball on a string and swinging it around in a vertical circle. So the diagram is shown to the right. And here we have a free body diagram when the ball is at the very bottom of the circle. So there are just two forces acting on the ball. The weight down, mg, and the tension in the string pulling upward. Since we're moving in a circle, we have an acceleration toward the center of the circle, which is the centripetal acceleration. That means the sum of the forces must equal m times the centripetal acceleration. This is just Newton's second law. Sum of the forces equals ma. So this case then, the acceleration is v squared over L. L is the length of the string, which is also the radius of the circle. So the sum of the forces equals mv squared over L. So since the acceleration is upward, I choose that as positive. So that we have the tension force upward minus the weight down equals mv squared over L. Now I solve for the tension, and we get the tension in the string equals mv squared over L plus mg. Mg is the weight. So we see that at the bottom of the swing, moving in the circle, the tension is greater than the weight by the term mv squared over L. So the faster we swing, the greater the tension in the string. Also note that the slower the ball moves, the less the tension, but the tension will always be greater than the weight mg. All right, and also note in the diagram, I have a yellow arrow with the A next to it. That's just showing the direction of the acceleration for reference. So be careful, acceleration is not a force, so we do not put that in the force equation. The only forces we have are the tension in the string upward and the weight downward. All right, let's look at what happens at the top of the circle. So as the ball goes through the top of the circle, we see we have the weight down, mg, and now the tension is also pointing down towards the center of the circle. And we still have our acceleration, of course, toward the center of the circle. So now when we apply Newton's second law, sum of the forces equals ma. Our acceleration is still the centripetal acceleration, v squared over L. So we have the tension plus mg equals mv squared over L. Solving for the tension, we get the tension T equals mv squared over L minus mg. So we notice here that at the top of the circle, the tension is less than it is at the bottom of the circle. But also notice that the slower we go, the less the tension is. And also notice here we have the tension equals mv squared over L minus mg. So we must be going fast enough so that mv squared over L is greater than or equal to the weight mg. If we're going slow enough where mv squared over L equals mg, at that point the tension is 0. And if we go slower than that, the ball will fall before it reaches the top. So we won't make it through the circle. So we have to be going fast enough where mv squared over L is greater than or equal to mg. So from this, we can see now what minimum speed we have to make it all the way around the circle. All right, so the minimum speed that we have to stay in a circle must be when the tension just goes to 0. So in the previous slide, we saw mv squared over L minus mg was the tension. So we must have mv squared over L must be greater than or equal to mg to stay in the circle. The minimum speed is when mv squared over L equals mg. The mass divides out, and so we get the minimum speed to stay in a circle equals the square root of lg. If we go slower than this, the ball will fall before it reaches the top of the circle. If we go exactly this, it will make it through the circle, but the tension in the string will be 0. And then if we go faster than that, we need tension in the string to keep it in the circle. All right, now what about the points when the string is horizontal when we're swinging in the vertical circle? So when the string is horizontal, the tension alone provides the centripetal force since the weight is straight down. So at that point, there's both a radial or centripetal acceleration and a tangential acceleration because of the weight. So in this case, the tension is mv squared over L, or T equals mac. And we have mg equals ma sub t, where a sub t is the tangential acceleration. So we will have both a centripetal acceleration and a tangential acceleration. All right, now let's look at another example. Hot Wheels are fun toys for kids. These are toy cars that can run on a plastic track. There's no motor or anything in the cars. They just run by pushing on them or by gravity. So here we have a track set up with a loop-the-loop. How fast must the car be going at the top of the loop in order not to fall from the loop? If the car doesn't go fast enough, it will fall out of the loop before it gets to the top. So it has to go fast enough to make it all the way around the loop and keep going. So what is the minimum speed that we must have at the top of the loop? Well, based on the previous example, we should know how to solve this. So with the figure at the bottom here, I've made the loop bigger so we can see the free body diagram for the car. So when the car is at the top of the loop, we have its weight down, mg, and we have the normal force of the track pushing it into the circle, also pushing down. And since we're moving in a circle, we have an acceleration toward the center of the circle, which is our centripetal acceleration. The centripetal acceleration, of course, we write as v squared over r. So Newton's second law, sum of the forces equals ma. In this case, a is v squared over r. So we have the normal force plus the weight equals mv squared over r. Okay, now the minimum speed will be just when the normal force goes to 0. So as we go slower and slower, we see that the normal force will get smaller and smaller. The weight, of course, is fixed by the car. So as we go slower, the normal force goes slower. So eventually we go slow enough, the normal force just goes to 0. And so at that case, we have mv squared over r equals mg. So that gives us the minimum speed equal to the square root of rg. The mass divides out. We multiply both sides by r and take the square root. So we have the minimum speed equals the square root of rg. Note, this is the same result that we got for swinging a ball in the vertical circle. At the top of the loop, the minimum speed had to be equal to the radius, but in that case, we called it L, the length of the string, times G. So it's the same result we had before for the balls being swung in a vertical circle. So if the car goes slower than this speed, it will fall off the track before it reaches the top. All right, let's look at one more example. There's an amusement park ride where you enter a circular room, a cylindrical shaped room that usually has a carpeted wall. And you stand with your back to the wall. And once everybody is inside, they close the door, they start to rotate the room. So the room is rotating around faster and faster. You start to feel like you're being pushed against the wall. Now remember, we are in an accelerated reference frame, which is a non-inertial reference frame. I explained these in another video with concepts of friction. All right, so in a non-inertial reference frame, we get these fictitious forces will show up. So while we're inside the room, we feel like there's a force pushing us against the wall. Well, if we stand outside the ride and look at the riders inside, we see that it is the wall pushing them into a circle. So the real force is the wall pushing the riders toward the center of the circle, keeping them moving in a circle. So there is no outward force. The real force is the wall pushing the riders inward into the circle. Okay, so what happens in the ride then, as you go faster and faster, they drop the floor down from underneath you, and you stay stuck to the wall. So you're stuck against the wall, and the floor is well below your feet, and you don't fall. All right, so why don't you fall? Well, because there's friction between you, your clothing, and the wall. So suppose the coefficient of static friction between the wall and your clothing is mu sub s, and the radius of the cylinder is r. What minimum speed v must the cylinder and rider have if the rider is not going to fall when they drop the floor? All right, so think about this. So again, this is Newton's second law. We're going to apply the sum of the forces equals ma. All right, so here in the lower diagram, I've drawn a free body diagram for the person pressed against the wall of the rotating cylinder. So just the little black rectangle represents the person. So since we're not sliding down, we have static friction holding us up. We have our weight down, of course. And so if we're not going to move, the static friction up must be supporting our weight mg down. Now we also have the wall is pushing us into a circle. So the normal force is the wall pushing us into a circle. And it's that normal force supplies the centripetal force that keeps us moving in a circle. So we apply the sum of the forces equals ma, and we do it in both the vertical direction and the horizontal direction. So in the y direction, we're not moving, we're stationary, we're not moving up or down. So we have the sum of the forces in y equals 0. So we have the static friction up minus our weight down equals 0. And in the x direction, the only force we have is the normal force pushing us into a circle. So that equals ma sub c, where a sub c is v squared over r, our centripetal acceleration. So we have the normal force equals mv squared over r. All right, so now we can get the coefficient of static friction, and we'll do that in the next picture. So we have the normal force equals mv squared over r. And then we also have that the static friction minus the weight, mg, equals 0. So we're going to assume that the static friction is at its maximum, so we can get the minimum speed necessary to keep us stuck to the wall. So the maximum static friction is the coefficient of static friction, mu sub s, times the normal force, and then that will equal mg, or the normal force equals mg over mu sub s. Well, now we know that the normal force is also mv squared over r. So we have mg mu sub s equals mv squared over r. Notice that the mass divides out, so it doesn't matter what our mass is. So we divide out the mass, and we solve for v, and we get v equals the square root of rg over mu sub s. So if we know the coefficient of static friction, we know the radius of the cylinder, g of course is the acceleration due to gravity, and now that gives us the minimum speed needed to keep us from sliding down and falling. Okay, so that's the end of this video. I'll do one more video involving centripetal force, and we'll look at a car going around a banked curve. But before we do that, if you like this video, please tap the like button and please subscribe. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.